Welcome back to an introduction to real analysis. We're now in chapter 5, section 1, the Riemann integral, specifically Riemann and Darboux integrals. Now, an integral is going to be a way to sum up the values of a function. It's worth stating that students, especially those who have only taken an elementary calculus course, are often confused about what the difference is between an integral and an antiderivative, or if there even is a difference. Now, the integral, informally for us, is simply the area under the curve of a function and not anything else. The fact that we may find an antiderivative by using an integral and vice versa is a very non-trivial result we're going to have to prove. We will be defining the Riemann integral, but actually using the Darboux integral. These definitions are equivalent. There are several exercises to illustrate that, but the Darboux integral is a technically simpler definition that lends itself better to the sorts of proofs we're going to be constructing. So we need to integrate a bounded function defined on an interval from a to b, including its endpoints. We're going to define two auxiliary integrals that will be defined no matter what for any bounded function. Only after defining these two things can we talk about the Riemann integral and the functions which it can integrate, the so-called Riemann integrable functions. So first, let's define a partition. A partition of the interval from a to b is a finite set x0 through xn, which are strictly increasing beginning at a and ending at b. So you select a finite collection of points. You have to pick the left endpoint a, you have to pick the right endpoint b, and you can pick some quantity in between, and you order them from left to right. Then we will denote delta xi as xi minus 1. This is simply the length of the ith interval, or the ith piece of the partition. Now suppose you have a function with domain the interval from a to b, including its endpoints. Suppose that function is bounded and you have a partition. Denote little m sub I to be the infimum of f of x on the interval from xi minus 1 to xi, including the endpoints, and capital Mi to be the supremum of f of x on that same interval. This is notation we will be very consistently using through this chapter. Capital P is a partition. The points in it are x sub I, big M sub I, and little m sub I are the sup and inf respectively of the function on the intervals created by the partition. So now we have a function f. Domain is the interval from a to b, including the endpoints. It is bounded, that is a running assumption, and P is a partition with little m and big Mi defined as previously done. Then we let capital L of the partition and the function to be the sum as I runs from 1 to n, in other words, over each interval of the partition, of little mi times delta xi, the inf of the function on a particular interval times the length of that interval. And capital U of p comma f is the sum over the pieces of the partition indexed from 1 to n, capital Mi times delta xi, the sup of the function on a particular interval times the length of that interval. We call these the lower and upper Darboux sums of the function with respect to the partition P. So the function f is fixed, but you need to specify a partition in order to talk about the lower and upper sums of that partition. Now the geometric idea of Darboux sums is indicated right here. The lower sum is the area of the shaded rectangles. Having made a partition of x0 through x8, on each interval, we can make a rectangle. The width is delta xi, the width of each interval. The height of the rectangles for the lower sum is given by the little m's, the inf of the function, whereas the upper sum is given by the capital M, or the sup. Now this picture is a continuous curve, meaning inf and sup are actually min and max, but in general, think of it as inf and sup. So the width, again, given by delta xi. Also note, these delta xi's do not have to all be equal to each other. In this picture, it appears that all of the intervals are of equal width. That is not a requirement. It's just a convenience when drawing pictures. So we move on to proposition 5.1.2. Suppose you have one of these functions f. It's a bounded function. Its domain is an interval, including the endpoints. Also assume that you have a lower bound little m and an upper bound capital M. Then regardless of the partition, the lower sum is always less than or equal to the upper sum. That's this inner inequality. However, the lower sum cannot be less than the overall lower bound little m times the width of the overall interval, and the upper sum cannot be larger than the overall upper bound capital M times the width of the interval. The proof of this partition is actually fairly straightforward, but it will be very useful for us. So suppose you have an arbitrary partition P. We're going to denote it as the points x0 through xn. Then, if you add up just delta xi, forget any little m's or big M's. Delta xi is simply xi minus 1, but we end up with what is called a telescoping sum. When I equals 1, we get a plus x1, but when I equals 2, we get a minus x1, which will cancel out this one right here. So various terms in this sum will cancel out, and the only thing that remains is the final plus xn and the first minus x0. But remember, for any partition, the last term xn must be the right endpoint b, and the first term x0 must be the left endpoint a. So regardless of the partition, if you sum up the delta xi's, you recover the length of the interval b minus a. Then, for each index I, because the ith interval is a subset of the overall interval, the set of values taken on that interval is a subset of the set of values taken overall. Therefore, the inf on a particular interval is bigger than or equal to a global lower bound, and the sup on a particular interval is less than or equal to any particular global upper bound. So we have established that if you add up the delta xi's, you recover b minus a. Every inf on a particular interval is bigger than or equal to whatever lower bound was established here in the setup of the proposition, and any particular sup is less than or equal to whatever this upper bound is. Then we simply establish this long chain of inequalities. The overall m times b minus a can be represented as this sum. This is now a constant as far as the sum is concerned and can be factored in, but every little m is less than or equal to any particular little m sub I. M sub I is the inf on a particular interval is always less than or equal to capital M sub I, the sup on a particular interval. However, each capital M sub I is less than or equal to this capital M, which is a constant which may be factored out. So overall, we have little m times b minus a less than or equal to the lower sum, less than or equal to the upper sum, less than or equal to capital M times b minus a. Okay, and those interior terms, again, are exactly the lower and upper sums, which completes the proof of the proposition. So what's really the purpose of this proposition, which was honestly fairly straightforward to prove? Consider the function in the interval to be fixed, and let script p be a set of all possible partitions of the interval, so all finite subsets of the interval which have to include the left and right endpoint. Now we can sort of construct these abstract functions L and U to be the lower and upper sum of each particular partition. We've just established that these functions are bounded. No matter what the proposition, the lower and upper sums are always bounded below and above by these fixed constants. So no matter what partition you create, you have this global lower bound and upper bound for whatever the lower and upper sums could possibly be. So therefore, the range of this lower bound function and upper bound function, which maps a partition to the lower and upper bound of that partition, these functions are bounded and therefore have an inf and a sup. Now, one choice of each of these is more interesting than the other. So we move on to our first real definition regarding integrability, definition 5.1.3. Suppose you have this bounded function on the interval from a to b, including the endpoints. Script p denotes all possible partitions. We can define the integral from a to b with a big line over it, f of x dx, to be the infimum of all possible upper sums. Similarly, the integral from a to b of f of x dx with a line under it to be the supremum of all possible lower sums. These are referred to as the upper and lower Darboux integrals of the function f. Note, They always exist. For any function f which is bounded on this interval, all upper and lower sums are bounded above and below, meaning the upper sums have an infimum and the lower sums have a supremum. So the existence of these things is not in question, provided the function f was bounded to begin with. Now the dx that we wrote before will probably not have raised any eyebrows, but it's also not necessary. We haven't defined what it is or what it means, and for this material, it is actually irrelevant and you can ignore it. So actually, we're generally just going to write this for the upper integral of f on the interval from a to b, and this for the lower integral of f. The of x dx is, at best, not necessary. Now, if integration is going to be a reasonable concept that we want to talk about, we would hope that these two quantities would be equal. And if they are, we would call that the integral. But these quantities, the upper and lower Darboux integral, are not always the same thing. So let's see an example. Let f be the Dirichlet function, one of our classic function that does bad things. This is the function that is 1 when the input is rational and 0 when the input is irrational. Then for any interval from a to b, we have the upper integral is b minus a, while the lower integral is 0. The proof is pretty short. Now for any partition, for any interval in that partition, that interval will contain both rational and irrational numbers. It is worth pointing out that our definition of partition required these x sub i's to be strictly increasing. So this interval does contain uncountably many points from the left to the right. It contains both rational and irrational numbers. So regardless of the partition and regardless of index I, the inf on that interval is 0 and the sup is 1. So for any partition, the upper sum may be computed as 1 times the length of the interval, but as previously discussed, when you sum up the lengths of the pieces of the partition, you recover the length of the interval overall, while the lower sum is simply the sum of 0 times delta xi, which will just be 0. So the upper and lower sums are constant. Every upper sum you could ever take is equal to b minus a, and every lower sum you could possibly take is 0. So it is quite trivial to take the inf and sup over upper and lower sums respectively. The inf over all upper sums is b minus a, because every upper sum is b minus a, and the sup over all lower sums is 0, because every lower sum is 0. So we have here an example of a function where the upper and lower Darboux integrals will not take the same value. Now, we have defined all previous terms for a function f defined on a fixed interval from a to b. Now, if f is defined on a larger set, for example, all real numbers, then for any particular interval from a to b, we can apply all the same definitions. What is important is that the function f be bounded on each interval, but not necessarily on its entire domain. We only required functions to be bounded on the interval where we are trying to define these things. For example, f of x equals x is not technically a bounded function, but on any particular interval you could pick, it is. So we have no problem writing something like this. Our definitions only allow us to write an upper integral if this function is bounded. F of x equals x is not bounded on its entire domain, but if we restrict ourselves to going just from a to b, it certainly is. Now, one very important tool in determining which functions will have the upper and lower Darboux integral equal to each other is going to be to consider what happens when we modify an existing partition by adding some points to it. So we refer to adding points to a partition as making the partition finer. This leads us to the following definition, a refinement. Let p and p tilde both be partitions of the same interval from a to b. If p is a subset of p tilde, we say that p tilde is a refinement of p. Given two partitions, p1 and p2, which may not be refinements of one another, if we simply take the union of both of them, well then, p1 and p2 are both subsets of this union, so we call it the mutual refinement of p1 and p2. This partition here. It is a partition. It includes the left endpoint and the right endpoint and a finite collection of points in between. Because it contains each of these, we can say it is a refinement of P1. It is also a refinement of P2, hence the term mutual refinement. Note that tilde P is a refinement of P provided P is a subset of tilde P. This was the definition. So tilde P contains every point that P had plus possibly more. That's why P1 union P2 is automatically a refinement of both, and in fact can be defined as the smallest set that is a refinement of both. Now it's important here that the interval from A to B is fixed and not changing. If you change the interval between two different partitions, none of this really makes any sense. So for example, here is a partition of the interval from 0 to 1. 0, a quarter, 0.6, 1. If we also add in 0.28, 0.9, and 0.99, but we still also have 0, a quarter, 0.6, and 1, we've made a refinement. We had a partition and we added some points to it. So proposition 5.1.7 is really going to get to the heart of what we're going to be using refinements for. Suppose you have a function, the running assumption being it's bounded on an interval from A to B, including the endpoints. P and P tilde are two partitions where P tilde is a refinement of P. Then what do we obtain? The lower sum of P is less than or equal to the lower sum of its refinement P tilde. Similarly, the upper sum of P is greater than or equal to the upper sum of its refinement P tilde. Now, as far as proving this goes, it's worth pointing out there is a middle inequality stated here, that the lower sum of P tilde is less than or equal to the upper sum of P tilde. We already covered this in an earlier proposition. For one partition that isn't changing, the lower sum is always less than or equal to the upper sum. Now, since partitions have to be finite, P tilde contains all points of P plus finitely many more points. So if we can establish the outer inequalities when we simply add one point to P, then by repeating this finitely many times, we could obtain the result we wanted. Okay. If by adding a single point, you always get inequalities moving in the direction you want, you can simply add one point, then another, and get to the end result. Similarly for the upper sums. So we're simply going to assume, without loss of generality, that P tilde is a refinement made by simply adding a single point, which we're going to call y. Now, since P tilde is obtained by adding a single point to P, if y was one of the original points of P, there's nothing to prove. P and P tilde are equal as sets, so their lower and upper sums are equal. So now let's assume that y is not an element of the original partition, in which case there is a unique index k, so that y is strictly in between xk minus 1 and xk. So here is the partition P that we started with, x0 through xn, and P tilde has all of the same elements, but in between these two elements we've inserted a new one, y. Now if I is less than or equal to k minus 1, or if I is bigger than or equal to k plus 1, the interval in the original partition appears exactly the same in the new one. So the sup on this interval will be the sup on this one, and so forth. So specifically, if we take the difference, L, the lower sum of the refinement minus the lower sum of the original, all terms will cancel except in the original partition, the interval from xk minus 1 to xk does not appear down here. And in the refinement, these two intervals do not appear in the partition above. So if we compute the lower sum of P tilde minus the lower sum of P, everything cancels except for the pieces of the partition in between xk minus 1 and xk. So here are our two partitions, P and P tilde. We just want to see what's going on in between xk minus 1 and xk. Now, in the original partition P, we don't need to change any notation because our notation is built around that partition. What we do need to change for P tilde, however, has to do with our choice of index. So the first interval goes from 0 to 1, the second interval from 1 to 2, but now the kth interval goes from k minus 1 to y. The k plus first interval goes from y to xk. Now the k plus second interval goes from xk to xk plus 1, and now our indices are just off by 1. So we're going to denote m tilde sub k to be the inf on this interval from xk minus 1 to y, and m tilde k plus 1 to be the inf from y to xk. Now, m tilde is at least as large as mk, but so is m tilde k plus 1, because this interval and that one, xk minus 1 to y and y to xk, are both subsets of xk minus 1 to xk. So the values taken by f on each of these smaller intervals are subsets of the values taken by f on the large interval. And if you pass to a subset, your inf can only go up. So the inf on the left piece and the inf on the right piece are both bigger than or equal to the overall inf. So here are our two partitions. Here are our infs on the two pieces of the refinement that don't cancel out when we take a difference. And here's sort of the picture, okay? From xk minus 1 to xk, we have broken this up into two pieces. This blue dotted line is the overall inf. On one piece, the inf will actually be equal, and on the other, it can only go up. Okay, so both infs are bigger than or equal to the inf we started with. So if both infs on these two small new created pieces in the partition are bigger than or equal to the inf in the original partition, if we take this difference, again, all terms cancel except those that involve between xk minus 1 and xk. So the only terms that survive in taking the difference are these two pieces from the lower sum of the refinement minus just this piece from the lower sum of the original. But now, m tilde k and m tilde k plus 1 are bigger than or equal to mk. So replace all of these with mk's, in which case this mk may be factored out, and you get a y, which cancels this minus y, a minus xk minus 1, which cancels this plus xk minus 1, and an xk, which cancels this minus xk. So the difference of the lower sum of the refinement minus the lower sum of the original is bigger than or equal to 0. That's exactly the claim on the left here. And there is an exercise that covers this inequality on the right. It's essentially the same argument. Some inequalities merely get reversed. Moving on to prop 5.1.8. Again, our same assumptions. F is a function bounded on the interval from a to b. If it's bounded, we're just going to pick a little m and a big M to be a global lower and upper bound, respectively. Then, global lower bound times length of interval, less than or equal to lower integral, less than or equal to upper integral, less than or equal to global upper bound times length of interval. Proof pretty straightforward. For any partition P, we have already established that we have this chain of inequalities where our left and right terms on this chain of inequalities are exactly what we want to have. Now, just look at lower sums. We have little m times b minus a is less than or equal to every particular lower sum. So the lower integral is the sup of all lower sums. So it has to be an upper bound on the lower sums. Any particular upper bound on the set of lower sums must be bigger than or equal to this particular lower bound on the set of lower sums. Therefore, the lower integral, the sup of the lower sums, and upper bound on the lower sums is bigger than or equal to little m times b minus a. And the right is exactly the same derivation. Okay, we actually already did the hard work, and hard is carrying a lot of weight here, in this chain of inequalities. Okay, so really you just take this here and pass to a sup of all these. Similarly, take this inequality and pass to an inf of all those. Which is to say it's the middle inequality that's really the point. The left inequality, the right inequality, those were pretty straightforward. It's the middle one. Let P1 and P2 be arbitrary partitions of the interval from a to b, and let P tilde be their mutual refinement. Then what we've already established is that by passing to refinements, the lower sum can only go up and the upper sum can only go down. Note I have P1 on the left and P2 on the right, but since P tilde is a mutual refinement, I get all of these inequalities. The middle one just saying the lower sum of one particular partition less than or equal to the upper sum. So for any particular partitions P1 and P2, we obtain this. The lower sum of P1 is less than or equal to the upper sum of P2. So now let's think way back to prop 1.2.7. If we have non-empty sets A and B, where every element of A is less than or equal to every element of B, then the sup of A is in fact less than or equal to the inf of B. So what do we have here? Every lower sum is less than or equal to every upper sum. So the sup of the lower sums is less than or equal to the inf of the upper sums, and we obtain that middle inequality we wanted to complete the proof of prop 5.1.8. Now we can finally define the Riemann integral. Now the Riemann integral can only be defined on a certain class of functions called the Riemann integrable functions, but as previously mentioned, we're actually using Darboux integrals and Darboux integration. The equivalence of the two notions is developed in the following three exercises. We're not focused on the exercises here. Just note, while we keep throwing out the term Riemann integral, Riemann integration, we're really doing Darboux integration. It happens to be exactly the same thing once you do those three exercises. So here is the definition of the Darboux integral. Let f be a bounded function on the interval from a to b, and suppose the lower integral equals the upper integral. Then you say the function is Darboux integrable, and this value, the shared value between the upper and lower integrals, is written as the integral of f from a to b. Now, by definition, any Darboux integrable function has to be bounded because the notion of upper and lower integral only existed for bounded functions. Now, because prop 5.1.8 gave us this chain of inequalities right here, where f of x is bounded below by m and above by capital M, we can immediately state the following. If you have a bounded function on the interval from a to b and it's Darboux integrable, and you have a global lower and upper bound, little m and capital M respectively, then whatever the value of the integral, it has to be in between the lower bound times the length of the interval and the upper bound times the length of the interval. A slight modification on the previous proposition. Suppose you have a bounded function f on the interval from a to b. Let capital M be an upper bound on the absolute value of f of x. Then the absolute value of the integral is less than or equal to that capital M times the length of the interval. Okay, moving on to an example. Suppose f of x is a constant function. Then we can in fact set a global lower and upper bound on the function to be the same value c. Therefore, by this proposition, the lower integral is bigger than or equal to lower bound times length of interval, the upper integral less than or equal to upper bound times length of interval. Since this global lower and upper bound are the same number, we in fact get equality throughout, meaning that the lower integral is equal to the upper integral. And therefore, the function is Darboux integrable, and the value of the integral must be the constant times the length of the interval. So constant functions are integrable. That's nice, but doesn't tell us very much. Let's look at another example. F is defined on the interval from 0 to 2, so that it goes from a value of 0 to 1 exactly at x equals 1, and at this point, you just choose to be this average value 1/2. We claim the value of the integral is exactly 1. It is integrable, first of all, and the value of the integral is 1. Now let epsilon be arbitrary, and I'm going to make a partition to go from 0 to just shy of 1, then to just above 1, and then all the way to 2. So here is our partition where these pieces are very, very close to 1. This is exactly 0. I put it slightly to the right so you can see the green line, and this is at exactly 2. Now, on the first interval, the function is constantly 0, so the inf and sup are both 0. On the last interval, the function is constantly 1, so the inf and sup are both 1. On this little piece in the middle, the inf is 0 and the sup is 1. Note, what's really important here is that we are not obligated to make these pieces the same width. We're very deliberately making the first piece of our interval and the third piece take up most of the domain. The single point at x equals 1 where the function does something non-constant looking, we're isolating in a very small piece of the partition. Now we can simply compute the value of the lower sum and the value of the upper sum. So we computed the value of the lower and upper sums for this specific partition where epsilon was an arbitrary number. and we find that the distance between the upper and lower sums is exactly epsilon. These two things, when I take the difference, cancel out, as do these. The only thing that doesn't is that intermediate piece. So, for any particular partition, the lower sum is less than or equal to the lower integral, because this was the soup of all lower sums. Similarly, the upper integral is less than or equal to the upper sum. Since these two things are now epsilon apart, and we have the upper and lower integrals must be in between them, and epsilon was arbitrary, we have that the distance between these two things is less than epsilon. For arbitrary positive number, they must be the same number. The upper and lower integrals are equal. The function is Darboux integrable. Now that we know the function is integrable, we can ask what is the value of the integral. Now, we already stated this chain of inequalities. However, we now know that this interior inequality is actually an equality. The function is integrable. For this particular partition, we computed 1 minus epsilon for the lower sum and 1 plus epsilon for the upper sum. Whatever the value is, it must be in between these, and since epsilon was arbitrary, we're done. The value of the integral from 0 to 2 must be exactly 1. Now, in the previous example, we made a very specific partition so that the difference between the upper and lower sums was as small as we wanted, an arbitrary epsilon. Can this technique be generalized to get a very useful result? Yes, and it's going to be our main way of showing that a function can have an integral. So the following result is more or less the major reason, at least in my mind, that Darboux integrability, rather than Riemann integrability, is the better starting definition for how we want to put together proofs, because this particular result takes a lot of groundwork for Riemann integrability, but we'll see it's actually not so bad for Darboux integrability. So here it is, prop 5.1.13. Again, we have a bounded function on the interval from a to b. Then f is Darboux integrable if and only if, for every positive epsilon, we may find one specific partition p so that the difference between the upper and lower sums is less than epsilon. So how are we going to prove this? If f is integrable, then the upper and lower integrals are equal to each other. Now let epsilon be positive. We can pick partitions p1 and p2 so that we have both of these inequalities. First, because the lower integral is the soup of the lower sums, if I take epsilon away from it, I am no longer an upper bound on the set of lower sums, meaning there is one particular lower sum bigger than this. Similarly, I can find one particular upper sum less than or equal to this. Now I can mutually refine the p1 and p2 we just picked to get in a partition p. We will see this value less than or equal to the lower sum of p1, less than or equal to the lower sum of this mutual refinement. For the mutual refinement p, the lower sum is less than or equal to the upper sum. However, the upper sum of the refinement is less than or equal to the upper sum of the thing it came from, p2, which was less than or equal to this upper integral plus epsilon. And now this lower integral and upper integral are in fact just the integral. So now what do we have? The lower sum and the upper sum for this partition P are in the same interval. The value of the integral minus epsilon, the value of the integral plus epsilon. So the distance between them is less than 2 epsilon. And of course, since epsilon was arbitrary, we could have begun with an epsilon over 2. Now that was half the proof. If the function is integrable, then we can find a partition with this property. The other direction was really the point. We want to say if I can find one partition with this property, then the function must be integrable. Let epsilon be positive and let p be a partition so that the difference between the upper and lower sums for this particular partition is less than epsilon. As we saw in a previous example, the lower sum of this partition less than or equal to the soup of the lower sums. The lower integral is always less than or equal to the upper integral, and the upper integral is less than or equal to one particular upper sum specifically for this partition. Since the distance between this lower and upper sum was less than epsilon, so too the distance between these lower and upper integrals is less than epsilon. And again, since epsilon was arbitrary, the lower integral and upper integral must be equal, and therefore by definition the function f is Darboux integrable. So let's look at a variant on example 5.1.14. We're going to show that f of x equals x is integrable on any particular interval from a to b. We will not compute the value of the integral. That's worth stressing. The previous result simply tells us if we can find a partition with a certain property, the function can have an integral, but it does not tell us how to find it. So let epsilon be positive and let n be very, very large, so that whatever b and a are, b minus a squared over n is less than epsilon. Since this numerator is a constant as far as n is concerned, the limit as n goes to infinity of this would be 0. So for sufficiently large n, it is less than epsilon. So just let n be large enough to make that happen. We're going to partition our interval into n pieces, where each element of the partition is given by this expression right here. Left endpoint a plus I times the total length over n. This means that each interval is of the same length, b minus a over n. If I have xi plus 1 minus xi, the a's cancel, and you have I plus 1 of this term minus I of them, making the difference just b minus a over n. This is what's known as a uniform partition, where every piece is the same length. All right, so we've made our uniform partition into n pieces. Each piece is of width b minus a over n. Now on each interval defined by this partition, because f of x equals x is just an increasing function, the inf is the value at the left endpoint, which is the left endpoint, and the sup is the value at the right endpoint, which is equal to the right endpoint, because f of x equals x. So we can now compute the upper minus lower sums. Here's the upper sum. We sum over all pieces of the partition, the value at the right endpoint, which is simply the right endpoint, times the width of that piece of the partition, minus the lower sum, the value at the left endpoint times the width of that piece. Now, a lot of simplification happens when I combine these sums. They're over the same range of index I, so I can just smush them into a single sum. They share this factor b minus a over n. Factor that out. You'll end up with a plus I times b minus a over n minus a plus I minus 1 times b minus a over n. The a minus a cancels out, and I have I times this width minus I minus 1 times this width, which gives me just b minus a over n, and I had already factored out a b minus a over n, giving us the following. The upper sum minus the lower sum is exactly b minus a over n times b minus a over n, or b minus a over n squared. But this is now being summed as I goes from 1 to n, and observe there's no I in what we're summing up. As far as the index I is concerned, this is a constant. What do you get when you sum up a constant n times? N times that constant cancels one factor of n from this denominator. And we specifically chose n to be large enough so that b minus a squared over n is less than epsilon. Therefore, the upper minus lower sums for this uniform partition on a great number of pieces is less than epsilon. Therefore, by our previous proposition, the function f of x equals x is integrable. So a remark, a way of thinking about the integral is that it adds up or integrates lots of local information. Okay, so f of x at a particular point is a local value. It tells you what is happening there, and integration integrates all of that information together. It smushes all that you know about values of the function at local points into some sort of global result about what is happening from a to b. Now the integral sign was chosen by Leibniz to be the long s. It came from a notion of summation, so that integral sign is supposed to be a stretched out s. Now, unlike derivatives, which are a local piece of information, the derivative of a function at a point is very much dependent on what is happening to the function nearby that point and only nearby that point. Integrals have to do with a more global perspective. What is happening at one particular point is not really the issue. You want to somehow collect together or integrate information about what the function is doing all the way from a to b. So this comes up when you are trying to answer questions about total distance traveled or average temperature or total charge of something over a region. Collecting a bunch of information about what is happening point-wise into a statement about what is happening in a region. That's the classic integral problem. Now, when f is defined on a set S, and the interval from a to b is a subset, We say that the function f is Darboux integrable on the interval if the restriction to that interval is integrable. A technicality that is barely worth stating. I mean, we were always talking about f being defined on an interval. What if it's defined on a larger set? Simply restrict your function to the interval in question and you're fine. Now, conflating Darboux and Riemann integrability, again, there are 3 exercises that help join this together. We say that f is in the set script r of the interval, and write the integral from a to b of f to be the value of this integral. That script r is coming from Riemann integrable functions. We have talked about Darboux integrable functions, but again, because some exercises show there's an equivalence, we're just going to talk about Riemann integrability. Now, it's also useful to talk about the integral from a to b, even when a is bigger than or equal to b. So you don't actually have an interval from a to b. So we simply define, if a is bigger than b, define the integral from b to a to be -1 times the integral from a to b. Also, if a equals b, in other words, you have a degenerate interval of a single point, it doesn't matter what the function f is, the integral from a to a of f is always taken to be 0. Now, if the variable of integration is important, some example might require you to really specify what variable of integration you're working with, it doesn't change the value of the integral. If you call the variable x or s or t, whatever. This d is telling you what the variable is named, and here you have the expression. So here you're saying x goes from a to b and you integrate f of x. Here s goes from a to b and you integrate f of s, and so forth and so forth and so forth. Clearly, renaming the variable doesn't really matter. When we are not particularly concerned with the name of the variable, we just leave it out, and that's the notation here, the integral from a to b of f. So we began with a sort of what I call a definition dump. What's a partition? What's an upper sum? What's a lower sum? What's the definition of Darboux integrability? Definition after definition after definition. But the most useful notion for establishing a bunch of our results was that of a refinement. If you have a partition and you add a finite number of points to it, you have made a refinement of the partition. And critically, refining a partition only brings the upper and lower sums closer in value. The lower sum can come up, the upper sum can come down, they don't cross each other. They don't have to change, note, but going to a refinement only brings these values closer together. We didn't formally define Riemann integrability, as I've said several times. The equivalence with Darboux integrability is established in some of the exercises, and we're not putting the exercises into the main body of these lectures.